Welcome everyone. Today, we'll explore how to solve linear recurrences using matrices and eigenvalues, focusing on an intriguing example with a second-order recurrence. Before we bring in matrices, remember that a recurrence is just a rule that turns earlier terms of a sequence into new ones.
Right now, I mostly think of them as number puzzles, like keep applying the same recipe to build the list.
You have already seen sequences, just ordered lists of numbers like a 0, a 1, a 2, and so on. A recurrence adds structure by saying how each new term is computed from previous ones.
So things like adding a fixed amount each time, multiplying by a constant, or adding the previous two terms all fit this idea.
Our plan is to reframe these number recipes as repeated linear transformations, so matrices and eigenvalues can do the heavy lifting for us. Next, we will grab one concrete recurrence and see how to turn its step-by-step rule into a matrix. Let us focus on one specific recurrence so we can see the linear algebra story play out from start to finish.
I usually try to look for patterns or guess a formula, but that feels a bit like trial and error.
Here is the rule we care about, together with its first two starting values.
So each new term depends on the previous two, and we know the first two entries of the list.
Our goal is to get a direct expression for a n, so we can jump to any term without computing all the earlier ones. Instead of pattern hunting or clever algebra guesses, we want a systematic method that works for many recurrences.
So somehow this number sequence is going to turn into taking a matrix to a power.
Exactly. We will package the recurrence as one linear transformation that we apply over and over. To do that, we first need a smart way to group the sequence values into a vector, a state that the matrix can act on. A key idea is to bundle a small chunk of the sequence into a single vector that we can update in one step.
So instead of looking at each single term alone, we track a pair of terms together as one object.
We define a state vector whose first entry is the next sequence term and whose second entry is the current one. This way, knowing Vn means we know two consecutive terms of the sequence at once. One step later, the new state just slides forward along the sequence, keeping the window of two terms.
So if the recurrence is linear, it makes sense that going from one state to the next should also be linear.
Yes, and a fixed linear rule on vectors is exactly what a matrix is built to represent. Now, let us write down the actual matrix that takes one state vector to the next using our specific recurrence. Now we translate the recurrence rule into a matrix that updates our state vector.
So each row of the matrix should describe how to compute one entry of the new state from the old state.
This matrix will take the pair of previous terms and output the next pair. This equation says that one application of the matrix turns the current state into the next state.
So the first entry uses the original recurrence rule, and the second entry just passes along the previous term.
The first row uses 4 times the current term minus 3 times the previous term to produce the new top entry. The second row simply copies the current term into the bottom slot, so our window of two terms slides forward.
So if I know the state once, I can keep applying the same matrix to march along the sequence.
The beauty is that doing many steps in a row now just means taking a power of this single matrix. Once we know the one-step matrix, repeated applications turn into matrix powers.
So instead of thinking step by step, we can jump straight to the nth step using a single power of t.
Starting from the initial state, taking the matrix to the nth power lands us directly at the state after n steps. Every time we move forward one position in the sequence, we apply the same linear transformation.
So doing n copies of that update in a row is captured perfectly by taking t to the nth power.
That means the heart of the problem is no longer the recurrence itself, but finding an efficient way to compute this matrix power. Next, we will bring in eigenvalues and eigenvectors, because they turn hard matrix powers into easy ones. Eigenvalues tell us how the matrix stretches special directions, and those stretches show up as exponentials in our sequence.
So if we know the eigenvalues, we are basically learning which exponential growth rates are hidden in the recurrence.
We subtract a variable times the identity matrix and take the determinant to get a quadratic equation for the eigenvalues.
Solving that quadratic, we get two eigenvalues, 3 and 1.
Those are the key numbers that will appear as powers in our final formula for the sequence. This determinant is what encodes the condition that the matrix has a non-zero vector that just gets scaled. Each root of that equation corresponds to a special stretch factor that the matrix can apply along some direction.
So I should expect our answer for a n to be some combination of 3 to the n and 1 to the n.
Next, we will find the eigenvectors that go with these eigenvalues, so we can put the matrix into a diagonal form. With the eigenvalues in hand, we now hunt for the directions that get scaled by those amounts.
These directions will become the new basis in which the matrix acts in a very simple way.
For eigenvalue 3, solving the system says that any multiple of the vector with entries 3 and 1 is an eigenvector. For eigenvalue 1, the solutions point along the line where the two entries are equal.
So we have one eigenvector pointing roughly toward 3, 1, and another along the diagonal line 1, 1.
Along this direction, the matrix simply multiplies by 3 each step, with no rotation or mixing. Along the diagonal direction, the matrix leaves the vector length alone, since the eigenvalue is 1.
That means any state vector can be written as a combination of these two special directions.
Since the eigenvectors form a basis, we can now build a matrix that changes coordinates into this convenient frame. Now comes the main linear algebra move. Rewrite T using the eigenvectors as a new basis.
This is where diagonalization shows up, with a change of basis matrix that turns T into something simple.
We build P by putting the eigenvectors as columns, and D by placing the corresponding eigenvalues on the diagonal. This relation says that in the eigenvector coordinates, the matrix T just looks like the diagonal matrix D.
Raising T to a power becomes easy, because taking a power of D just means raising each diagonal entry to that power.
This is the payoff of diagonalization. Hard matrix powers reduced to simple scalar powers. P is the bridge between the original coordinates and the eigenvector coordinates. D captures how each eigendirection is scaled when T acts once.
So to understand the recurrence for any n, I really just need to understand powers of 3 and of 1.
Next, we will plug in the actual starting values and see how the state decomposes into these eigendirections. To use the diagonal form, we first need to express our starting state as a combination of the eigenvectors.
That means solving for how much of each eigenvector we need to add up to get the initial pair of terms.
Our initial state vector bundles the first two values of the sequence into one column. We look for numbers alpha and beta so that a combination of the two eigenvectors reproduces this initial state.
Solving the two equations in alpha and beta gives alpha equal to 5/2 and beta equal to -1/2.
So the initial state is a mix of mostly the 3 eigenvector direction with a small negative amount of the 1 eigenvector direction. This is just expressing the vector in the eigenvector basis instead of the standard basis. Because our space is two-dimensional, we end up with two simple linear equations to solve.
Once we know these coefficients, we can just let each eigenvector piece grow by its own stretch factor each step.
Next, we will run this combination forward n steps and read off a direct formula for the sequence terms. Now we let each eigenvector component evolve for n steps and then extract the term an from the state vector.
This should turn our matrix story back into an explicit formula for the original sequence.
After n steps, the part along the 3 eigenvector gets multiplied by 3 to the n, while the part along the 1 eigenvector stays the same size.
Plugging in alpha equal 5/2 and beta equal -1/2 gives a concrete expression for the whole state vector.
Looking at the second entry of the state vector yields the closed form for an as 5 times 3 to the n-1 all over 2.
We can quickly check it. For example, at n equals 0 it gives 2, and at n equals 1 it gives 7, which match the initial values.
This is why exponentials appear, because repeated scaling by the same factor accumulates as a power. The sequence values sit in that lower coordinate of the state, so we simply read that entry off.
It is cool that the answer is exactly a combination of the eigenvalue powers we saw earlier.
Now that we have the explicit formula, we can step back and see how eigenvalues control the overall behavior of the recurrence. Let us zoom out from this one example and think about what eigenvalues tell us more generally.
I want to connect the algebra of eigenvalues with how the sequence behaves over the long run.
Because each eigendirection scales by its eigenvalue each step, its contribution to the sequence looks like that eigenvalue to the n. When you combine several exponentials, the one with the largest magnitude tends to win as n grows large.
If all the eigenvalues are smaller than 1 in size, then their powers shrink and the sequence dies out.
If there is an eigenvalue with magnitude bigger than 1, its component grows quickly and drives the sequence to blow up in size. When eigenvalues are complex, the sequence often oscillates like a sine wave, while also growing or shrinking overall.
So, a linear recurrence is really a tiny dynamical system, and the eigenvalues are its long-term personality traits.
You might have seen another standard way to solve linear recurrences that looks more like a clever guess.
Yes, where you assume the answer looks like r to the n and solve for r, then combine the solutions.
The traditional algebraic trick is to plug in a guess that each term is some base r to the n and see what r values work. Our matrix approach packages the same idea into linear algebra language, using eigenvalues and eigenvectors instead of pure symbolic guessing.
So the characteristic equation for r is really the same as the characteristic equation for the eigenvalues of t.
The linear algebra viewpoint not only solves the recurrence, it also gives a picture of vectors being stretched and rotated step after step. Now let us peek at a slightly more advanced example where complex eigenvalues create oscillations. Some linear recurrences lead to complex eigenvalues, which brings trigonometry into the story.
So we can get sequences that wiggle up and down rather than just growing or shrinking smoothly.
For this recurrence, the associated matrix has a pair of complex conjugate eigenvalues. The general solution can be written as a radius to the n times a combination of cosine and sine that depends on n times an angle.
So the sequence both oscillates because of the trig functions and grows or shrinks because of the radius to the n factor.
Even with complex eigenvalues, the starting point is still to write a transition matrix for the state vector. The only difference is that the quadratic or higher degree equation has roots that are not real numbers.
It is neat that a discrete recurrence can secretly encode circular motion through these trig functions.
You do not need all the details of the complex case yet, but it shows how powerful the linear algebra viewpoint can be. Before we wrap up, let us summarize the main steps in turning a recurrence into a matrix power problem.
I want a checklist I can follow the next time I see a linear recurrence.
First, group a few consecutive terms into a state and figure out the matrix that updates that state in one step. Second, solve the characteristic equation to get eigenvalues and then find the corresponding eigenvectors.
That gives a nice change of basis where the matrix just scales the coordinates independently.
Finally, use the diagonal powers to compute the state after n steps, and then extract the sequence term you care about.
It is satisfying that this one framework works for lots of different recurrences, not just the example we did today.
Let us cement the idea with a quick practice problem that follows the same pattern.
I will try to talk through the steps and see if I can predict the closed form.
Here is a similar second-order linear recurrence with two starting values. If you set up the characteristic equation, you get a quadratic with roots 1 and 2, so the general form is a times 2 to the n plus b times 1 to the n. Using the initial values, you solve a plus b equals 1 and 2a plus b equals 3, which gives a equal 2 and b equal -1, so bn equals 2 times 2 to the n minus 1.
That matches the matrix view, because the eigenvalues of the transition matrix would also be 1 and 2. For me, it is less about guessing and more about understanding how a linear transformation pushes a state around over time.
As you keep studying linear algebra, you will see this same idea appear in differential equations, Markov chains, and many other dynamical systems. Great work today, and keep an eye out for recurrences hiding inside linear transformations in other contexts. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.